Okay, we're going to look at how do you solve quadratic equations by using square roots. First thing we have to explore is what does a square root even mean? Well, if I had a problem like h squared equals m, and I wanted to solve it for h, in order to get rid of the square, I would square root both sides. Now notice we end up with two answers. H would be equal to the square root of m, and h would be equal to the negative square root of m. The reason that is because we don't know if it's going to be positive or negative. And let me show you what I mean. If I asked you what the square root of 9 is, most people would probably say 3, because they know that 3 times 3 gives you 9. But it could also be negative 3, because negative 3 times negative 3 also gives you 9. So when we take the square root, we got a positive answer and a negative answer. And that's what this is telling you up here. We could have a positive or we could have a negative answer. And that's when you apply the square root. Okay, what I want you to do is to take your calculators and type in the square root of 15 and see what decimal it equals. Then I want you to type in the square root of 5 times the square root of 3. Notice that 5 and 3 are both factors of 15. Then I want you to type in the square root of 5 times 3. Make sure the 5 times 3 is all underneath your radical. I want you to make a mental note about the decimals for each one of these things. Then I want you to do the square root of 10 plus 5. Make sure the 10 plus 5 is all under the radical sign. And I want you to compare that to the square root of 10 plus the square root of 5. And make a note about what the values of those were. Hopefully what you noticed was that these were all equal. And I use this example to show you that when we have a number, we can break it down into its factors and not change its values. But we can't take that number and break it down into an addition problem. So even though 10 plus 5 would still give us a 15, we can't break it down into an addition problem. We can break it down to multiplication, but not to addition, because it doesn't equal out the same way. Okay, do the same thing with these two examples. Look at the square root of 3 over 5 and make sure the 3 divided by 5 is all under the radical. And then look at the square root of 3 divided by the square root of 5. Okay, make a note about what you noticed about their values. Then try this example. I've got the square root of 8 minus 3. 8 minus 3 all needs to be inside the radical sign. And then compare that to the square root of 8 minus the square root of 3. And again, hopefully you noticed that these top ones were equal. These bottom ones are not equal. So when we have a division problem, we can break it up into its individual pieces. But now when we have a subtraction problem, we cannot break it up into individual pieces. It does not work. What we're going to look at first is what's called rationalizing a fraction. And it's not acceptable to leave a radical in the denominator of a fraction, so we have to rationalize it when necessary. Now keep in mind, a radical is any type of root. We're going to go ahead and do a simple example. Let's do 3 over the square root of 2. Now the problem with this is I have a radical in the denominator. And what I want to do is I want to multiply this fraction by some value of 1 so that I no longer have a radical in the denominator. Now the reason we have to multiply it by a value of 1 is so we don't change its value. And remember, you can write any fraction like 3 over 3 is equal to 1. 1/2 over 1/2 is equal to 1. So as long as whatever we have on the top is the same as what we put on the bottom, we're going to have a fraction that's equal to 1. Now for this particular one, what we want to do is we want to get the number inside here to be a perfect square. Well, in order to do that, I'm going to multiply it by the square root of 2 over the square root of 2. When I multiply that, the top becomes 3 square roots of 2, and the bottom We just got done showing that when it's a multiply problem, I can go ahead and do this. I can multiply them together. So that would turn into the square root of 4. You might be looking at that thinking there's still a radical sign in it, but what is the square root of 4? It's a 2. So we've turned it into a perfect square, which allows us to get rid of the radical in the denominator. So our answer for this rationalized problem would be 3 square roots of 2 over 2. Let's do another one. Let's say I had 2 square roots of 5 divided by 3 square roots of 3. Now with this one, I've got a radical in the numerator and a radical in the denominator, but the only one that's causing the problem is the one in the denominator. So I need to multiply by the one that's causing the problem, which is the square root of 3. So I'm going to multiply the top and the bottom by the square root of 3. And when I do that, I end up with 2 times the square root of 5 times the square root of 3 over 3 times the square root of 3 square root of 3. Now when I simplify this, since the 5 and the 3 on the top are both radicals, I can go ahead and multiply them together. This is the example we did just previously. 3 times 5 is 15, so the top really becomes 2 square roots of 15. Similar thing happens on the bottom. Since it's a multiply problem, I can multiply them, and I can get 3 square roots of 9. Well, from here, I know that the square root of 9 is 3, so I'm going to have 2 square roots of 15 over 3, and then that square root of 9 changes to a 3. Well, I can simplify that one more time to this 2 square roots of 15, and then 3 times 3, since they're both regular numbers, is 9. Now the reason I can't multiply the 2 and the 15 together is because the 2 is not a radical, and the 15 is a radical, so they're not the same type of numbers. So they have got to stay separate. So that would be how we rationalize. Next thing we're going to look at is how do we simplify radicals? And what we want to do is we always want to look for a factor that is a perfect square. Now keep in mind our perfect squares would be 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. You'll want to have the list of perfect squares handy when you are simplifying your radicals. It'll help you go a little bit faster. So what we want to do is we want to break these down. And we do that by looking for a factor that is a perfect square. So a factor means a number that we can divide into it. So factors of 45 would be 1 and 45, 5 and 9, 3 and 15. But we don't just want to pick any factors. We want to pick a factor that's a perfect square. So what I'm going to do is I'm going to go over to my list of perfect squares, and I'm going to figure out what off of this list goes into 45. Well, I don't need to go any higher than 49 because that wouldn't make any sense. And I want to start working my way backwards. So I want to see, is 36, does that go into 45? Does 25 go into 45? Does 16? Well, 9 is the first one we get to. So when I do this, I'm going to break it down into the square root of 9, and then I know that 9 times 5 will give me the 45. So it's going to be the square root of 9 times the square root of 5. Then I can go ahead and simplify this because I know that the square root of 9 is a 3. So this would simplify into 3 square roots of 5. Now one way that you can check to see if this was right is you can take your calculator and type in the square root of 45 and see what decimal you get, and then type in 3 times the square root of 5 and you should get the same decimal. Okay, let's try the 75. I'll extend our list of perfect squares here. And since I've gotten to a number bigger than 75, I don't need to check any higher. So I want to see, can I divide 75 by 64? Can I divide it by 49? 36? Okay, 25 is my first one I can divide it by. So I'm going to break 75 down into 25. And I know that 25 times 3 is what's going to give me that 75. Then I know the square root of 25 is just a 5. So I would end up with 5 square roots of 3. Okay, now let's look at 80. Well, I don't need to go past this number right here because it's bigger than 80, so I want to start working my way back up. Can I divide it by 64, 49, 36, 25? I believe it's 16. So we want to break 80 down into the square root of 16 and the square root of 5. Now, when I break the square root of 16 down, I get 4 square roots of 5. And then to check, you could type in the square root of 80 and then 4 times the square root of 5 and see if it works out. Now, let's say you didn't realize that 16 went into 80 right away, and you went straight to the 4. Well, we can still work with that. So the 80, it would have broke down into the square root of 4 and the square root of 20, and you would have gotten 2 square roots of 20. But what you would have had to notice was that 20 could be broke down by the 4 again. So you would have had to break that down into the square root of 4 and the square root of 5. So you would have ended up with 2 times the square root of 5, which brings us to that 4 square roots of 5 we had before. So even if you don't recognize the biggest one right away, you can still get to the correct answer. It would just take multiple steps. Okay, so here's some practice ones. We are going to rationalize, we're going to simplify, we're going to do all that for each of these problems. So the first thing I've noticed is that I've got a radical in the denominator. So I'm going to take care of that by multiplying by what's causing the problem. When I do that, I get on the top the square root of 16 over the square root of 4. And now this one's a really nice one because the square root of 16 is 4. The square root of 4 is 2. 4 divided by 2 is 2. So this one actually just turns out to be the regular number 2. Next one, square root of 24 over the square root of 5. I'm going to multiply by the square root of 5 over the square root of 5. And on the top, I am going to get the square root of 120 divided by the square root of 25. And the square root of 25 is 5, so I'm going to have the square root of 120 over 5. So we've gotten the radical out of the denominator. But now we have to check, can I break the 120 down? So if you look back at